Okay. Yeah, I think that should do it now. Okay, I think that should do it. Yeah, so now example 9.5. So oil and water, right? So basically what we are looking at in this question, remember we discussed last time we made to say, yeah, so we discussed the last time that we made to say uh with regards to pressure, pressure increases with depth, right? So if pressure increases with depth, if we've got a situation as this, we know that the pressure is going to be the most, or is going to be highest where at the bottom, right? So at the bottom, that's where you're going to have the highest pressure. Now there's pressure that's happening on, there's atmospheric pressure, then there's pressure due to the oil, and then there is the water. So then how then do you go on to answer this question? Basically you're just saying the pressure that is on top, that's atmospheric pressure, the one that we usually like to call PO, isn't it? To just say it's that it's the first atmospheric pressure, of course, that you're going to have because of because of just air, isn't it? Because of atmospheric air rather. Then now, so that's about it. Then now you want now to find what pressure was being caused by the depth of the oil. So you know that the depth of the oil there is what? So the depth of the oil, you see that it's yeah, it's that H1 there, right? So that means that the pressure which is acting on top of the water, okay, so on top of the water, the pressure that you are getting is P1. Why are you getting a pressure of P1? You are getting the pressure of P1 because this is the atmospheric pressure plus the pressure that has been added due to the depth. You get that point, right? So yes, there is the pressure, yes, we agree. So there is that pressure, but then what is happening is that there is also as you are going down there, you are getting what's this you are getting an increase in pressure. Then the pressure that's now at the bottom of this particular tank, or the tanker that you are looking at, the pressure that's going to be there is going to be the one, it's going to be P1 plus the pressure due to the H2. That makes sense, right? So that's basically just how we are going to do it. So now the question is telling us, in a huge oil tanker, salt water has flooded an oil tank to a depth of so that's 5 meters, right? So the water, the H2 is 5 meters. On top of the water is a layer of oil, 8 meter deep, as in the cross section of view of the tank in that figure 9.14 that we are looking at. The oil has a density of 0.7 zero point 0.7 grams per centimeter cube. Find the pressure at the bottom of the tank. And they've given us that density that we're supposed to use for salt water. So basically here, it's what I've just explained. So we're just going to do it, right? Yeah, so we're just going to do exactly what I've explained. So what you want to look at is, okay, yeah, so what you want to look at is you want to start it with this. Okay, so you say, okay, so you're going to say uh P1, okay, is equals to P0 plus PGH, okay, of which if you want to be specific, you can say PGH1. Huh? So we're now going to say P1 is going to be our pressure, P0 is our atmospheric pressure, right? And we know that atmospheric pressure is 1.01 times 10 to power 5 pascals, isn't it? Then plus PGH. So P, okay, for me, I just like calling it P so that I don't forget, but I know that it's actually density, okay? Yeah, like I feel it's easier when I call it like that, right? So now you may have looked at that density for oil. So we have to convert it to what? We have to convert it to kilogram per millimeter cube. So when we do that conversion, we are going to get 700 kg per meter cube. So we are going to get 700 kg per meter cubed. You remember that when we were looking at units and measurements, we looked at how to convert these things. Also, to save on time, we just write it like that. Then G, we have the G. Then now the depth. Then the depth is what? The depth is 8 meters, right? So this means that this PGH, this density times gravity times height, is now giving us the value by how high of the change for which this pressure is going to have, right? Higher than the atmospheric pressure. So then what you're going to have is that, and that. So it's going to be 1.56 times 10 power 5 pascals, isn't it? So there you have. So that was the pressure that the oil was having on the water, isn't it? Now you want now to proceed and to be able to answer now for the pressure which was being caused, or the pressure that the water actually had, you know, at that bottom, right? At the bottom of this tanker. And so you will realize that the pressure was it's going to get higher, right? So what we are now going to do is we're now calculating for P2. If you want to say P2, or if you want to say pressure at the bottom of the tanker, right? It's still the same thing. So what you're going to say, you're going to get your P1. Now, here is the catch. Why are you getting your P1? Because you are now getting the pressure which is on top of the water surface. So you're not going to get something that was the P0. No. You are now getting the pressure which is on top of the water, right? So the pressure that is on top of the water is the P1 that we calculated, and not the P0. So once you've gotten that, then you're going to have the density, gravity, and the H2, isn't it? So now this one now is one that's now going to give us by one margin. This is what this is increasing, or by what margin it is changing, isn't it? Great. So now we write the one that we found, 1.56 times 10 to power 5. So we have that. So okay, so that's Pascal. Then now here again we are looking at something different, right? We are looking at water. So water, the density is 1025. Okay, yeah, you would write that, or if you want to write it a shorthand. So I prefer the shorthand. So it's going to be 1.0525 times 10 to power 3. So there you have it, like that. Okay, then times 5 meters. So this 5 meters, then now we are now going to find the value, which is going to be 2.0. So maybe someone may be wondering to say, but why didn't we just get the total height, the 8 plus 5 meters, and then just use the equation directly? Well, we could have done that to find a quick answer if and only if we had the same substance. What I mean is, if this oil tanker only had oil, then we could have just calculated the total distance, right? From the top to the bottom. But because there were two different substances with different densities for that matter, right? So that's why we had to go down the route of us having to so that's why we had to go down the route of us having to calculate them separately. Okay, so that's really the thing there. Okay, so now I would want to, then we now want to talk about the Pascal's principle. So I'm sure you may have been, you may have, you've seen where you take a car for repair, and then it's able to be moved up, and then you're wondering how is this happening. So the principle that works there is what? It's the Pascal's principle. So this is the understanding that any increase in pressure at the surface must be transmitted rather to every point in the fluid. So what this basically means is, if I've got a container, right, and then let's say I put pressure on top of the container by either maybe blowing some heavy air, down into the container. What Pascal's principle is just basically saying is that the pressure that has been placed at the surface of that fluid is going to be transmitted up to the what? Up to the bottom of the fluid, right? That's why if someone puts, let's say, a sachet of water on their head, and then someone hits the top of the sachet of water, what's going to happen? The person will still be able to feel the pain. So just picture this. I get a sachet of water and I put it on top of my head. Then someone hits the top of the sachet that's on top of my head with some pressure. And what's going to happen? I'm going to feel the pain to some extent. So why have I felt the pain even though the sachet is on top of my head? I felt the pain because the pressure that was increased at the surface of that water sachet has been transmitted into every point of the fluid, and so I've been able to feel the pain. So now, this is what Pascal's principle talks about. But now, that was just in understanding, right? But the actual principle says a change in pressure applied to an enclosed fluid is transmitted and diminished to every point of the fluid and to the walls of the container, right? So what this basically means is if there's a change in pressure to an enclosed fluid, right? So why is enclosed important here? Because if it's open, basically the pressure is just going to go out. It's just going to go somewhere out, and you won't be able to harness that particular pressure. So again, that's something that you want to take care of, isn't it? So it has to be an enclosed system with a fluid, and so the pressure is going to be what? Is going to be transmitted and diminished, meaning each and every particular point is going to get its equal share of that pressure, right? That's if we could use that word. So now the application where we use this, of course, like I mentioned, it's in hydraulic lifts, okay, but also in hydraulic jacks. I'm sure you've seen how a small jack is able to lift the car and everything. But the point here is the Pascal's principle. So what happens basically here is, so you see there on the left, we've got a small force F1 is applied where is applied on the left and produces a much larger force on the right. So what's happening here? What's basically happening is that here on the left, we've got that force that has been applied. Now what's happening is that, remember, we are saying the pressure in an enclosed fluid is transmitted and diminished, okay, is transmitted and diminished. So this means that an increase of pressure in the smaller area is transmitted to the larger area. But because force equals pressure times area, it means that, you see, now we're now taking the force to the larger area. So therefore, what you're going to get at the F2, or the second force, the one that's lifting the car, is what? Is larger than the force which was actually uh used in the beginning to start this hydraulic lift. But the take home point is, what Pascal's principle is saying is that this small force, the force that was exerted here, it has to be transmitted throughout this system. And when it comes here, because now the area has increased, the volume has increased, but it still has to be transmitted to what? To every point and diminished. And so because it's being transmitted, and then the surface area increases, then you see that the force is going to be what? It's going to be increased. Now, this is by a factor of what? A factor of area 2 over what? Over area 1. So basically, don't worry, we'll be able to look at an equation just for us to appreciate that. But basically, this is about Pascal's principle. Okay, so maybe let me just explain why I'm saying we are going to have that particular uh why I'm saying you're going to have that particular ratio, right? So we are saying So what's going to happen now? We know that the pressure, okay, so the pressure on each of the pistons is going to be the same. Okay, so the pressure is going to be conserved. Huh? So the P1, so meaning the pressure on the smaller one, and the P2 is going to be the same, because it's just changing because the the force is changing, right? Oh, sorry, not the force. The area is changing, right? So because the area is changing, therefore the magnitude of the force 2 is larger than the magnitude of force 1 by the factor of area 2 over area 1. So this is what basically means. So we know that pressure is equals to what? Pressure is equals to force over volume. So this is going to be F1 over A1, and this is going to be F2 over A2. So when we talk about the ratio of the F2 to F1, we are talking about cross multiplying, isn't it? So cross multiplying, we are going to get A1, also F2 A1, F1 A2. So to find the ratio for this, what are we going to do? So we divide both sides by A1, both sides by A1. So therefore, that's how they are getting that ratio to say the ratio is going to be A2 over A1 and then the force F1. So that makes sense, right? So yeah, so basically that's how those relations, and of course you can do the same for the F1, right? Just use those principles. So before we can look at examples, and then we can talk about the Archimedes principle. Um, are there any questions on this concept of the Pascal's principle before we look at an example? Okay, so if there is no question, then we can now look at this example. So we are looking at the car lift, right? One of the uses of the Pascal's principle or application of the Pascal's principle. So in a car lift used in a service station, compressed air exerts a force on a small piston of circular cross section having a radius of so R1 5 centimeters. This pressure is transmitted by an incompressible liquid. So why is the incompressible word important? It simply means that this is a fluid where you can't compress. So because you can't compress it, all the pressure is going to be transmitted evenly throughout the system, right? So that's why that word is important there. Okay, so so what force must be must okay, I think I've gone way ahead of myself. So this pressure is transmitted by an incompressible liquid to a second piston of radius R2, which is so R2, which is 15 centimeters. What force must the compressed air exert on the small piston in order to lift a car weighing 13,300 newtons? Neglect the weight of the pistons. Okay, so then B, what air pressure will produce a force of that magnitude? And then show that the work done by the input and output pistons is the same. Okay, so so we are going to answer this. So the first question is, what force must the compressed air exert on the small piston in order to lift a car weighing? So remember, the piston, we designate it as what? As one. So that small piston, like where everything else is starting from, we designate it as one. So it's going to be R1 for radius, it's going to be A1 for area, it's going to be F1 for force, P1 for pressure, right? So we designate it like that, right? Okay, so what this then means is we know, like we discussed, we said P1 go to P2 F1 over A1 is equals to F2 over A2. And then what then you're having here is, now we've been given the radius, right? You've seen we've been given the radius. So but because before we can complicate our work with the radius, what you want to look at this point is to be able to make F1 the subject of the formula, because they are telling us, say, what force must the compressed air exert on the small piston in order to lift a car weighing 13,300 newtons. So what this basically means is our F2 is what we are trying to carry, isn't it? So it's that 13,300 newtons. So we make F1 the subject of the formula. Then this is going to be A1 over A2, and then this is going to be F2, right? So that's about it. Now we know that we've got red in this question, right? So we want to change our equation further just to be able to accommodate that, right? So we're going to say F1, the area, we know area is going to be pi r squared, right? So we're going to say pi r, again 1 squared, right? Okay, then we've got pi r 2 squared. Okay, then we now have f2, isn't it? So now we now come here and say, so the pi, so for r, so that was what, that was 5 centimeters, but you always convert to meters, right? So once you convert it to meters, you are getting, so you're getting that. Then the larger piston was 15 centimeters, so converting to meters, you are getting that. And then yeah, so you're getting that. Then the F2, so the force we are trying to carry is that. Okay, so that's the force that we are trying to carry. So then we are going to have that, and then we are going to have a value of 1.48 times 10 to power 3 to power times 10 to power 3 newton. So that's the force that should be applied on the small piston if we are to have what, if we are able to be able to lift that particular car. So that's something that's important to take note of. Okay, okay, so that's something that you want to do. So having done that, what else? So that's the first part, right? I don't know if there are any questions, please ask. So now we now want to calculate what the pressure of this force, what the air, because remember here you are using air, right? You are using air pressure. So we've gotten that, but we've gotten the force, but we want to find what the pressure is. So this one really, it's where you say pressure is equals to force over area. So you have the force, the one that we calculated. So there you have it. Then you have that over. So the area again, pi r squared. So this is a small piston. So it was 5 centimeters. You convert it to meters, isn't it? Can you just write it properly? So you convert it like that. Don't forget the square. Then your answer is going to be 1.88 times 10 to power 5 pascals. So that's how you do it, right? Yeah, so we've gotten that air pressure. So that was the air pressure that was being applied. Then now, for a more technical question, I would say showing that the work done by the input and output pistons is the same. Now, here, one thing that's important is don't memorize this. So, the approach that I would want us to take is, like I've always been saying, don't memorize this, right? So, what first do you want to do? You know that the work is going to be the same by okay, so the work done by the input and output pistons is the same. So then you want to be able to reach at a point where you can be able to show that. So first of all, you are going to look at the volumes. So the volume of let's say the volume of the fluid that's being involved is the same, right? So there's nothing like no, there's an increased, this no. The volume that's going to be in the system is going to be the same, right? So that's the place where you would want to start from. So what you're basically saying is that the V1 and the V2 is the same volume. It's just that we're just designating them differently because of the larger and the smaller piston, isn't it? So that's a cardinal starting point that you want to start from. Then from here now, how then can we relate this volume to something that we already have? What we already have is what? Is area. So you're saying, okay, how can I rewrite this volume in terms of what? In terms of area. So you say volume is equals to area and that and the change. Okay, so that and then the change in distance. Or if you want, it's just area times what? Area times, if you want, times height or anything, right? But for now, we're just going to say times that distance. They are changing distance, right? Yeah. Then for the V2 again, it's the same thing. Area times a distance, isn't it? Don't we say area is equals to, sorry, volume is equals to area times height? So that height is just a distance, right? So that's about it. So now, after we've done this, then we now want to write uh this particular area. What we can, yeah, so from here now we can say, okay, let's now write it a little bit neater, right? So to write it a little bit neater, I'll say, okay, let's uh let's put the areas on one side and put the other things on one side, right? So that we can achieve that. So what you want to do at this particular point is say, so I'm going to say so that, yeah, so I'm going to ensure that I say, so you cancel, so you put that there, and then you want to put that there. Okay, that, then A1, and then A1. So here you just want to write things. So this cancels that. So what you're going to have is change in distance 1, change in distance 2. Then you're going to cancel that. Then you're going to have area 2 and area 1. So that's our first thing that we've derived. So let's just follow through. Now, we know that there is a relationship between the forces that we have in Pascal's triangle, isn't it? And these, they are related by the what? These are related by by the areas. So remember we said, and this is that I'll just okay. So remember we said P1 is equals to P2. So this is going to be what? This is going to be F1 over A1, F2 over A2. Okay, so that's about it, right? Yeah. So there you have that, right? Then after this, now you now want to do the same. You want to put the forces together and the areas together. So what you do here is, okay, let me divide both sides like we did there. So what you're going to do is you're going to say, okay, let me divide. So you're going to say, okay, let me get F2 here. I divide by F2, then F2 there, right? So meaning when I cancel that, what am I having? So I'm having F1, F2, A1. Okay, then there is that. Oh yeah. So now if you want now for this, if you want, you would say multiply through by A1, isn't it? So when you multiply through by A1, so you are cancelling that for that one. So you're having F1 over F2, then you are having A1 over A2. So you've gotten that one there, right? Okay, so now let's just wind up on this question. So now we know that what are we comparing? We are comparing the wake, right? So we know wake one.
So just repeat on the previous page.
Yes, yes, you can ask.
If you shot the previous page screen.
Yes.
Okay, thank you.
Okay, you're done.
Yes.
Okay, great. Okay, yeah. So so I know maybe perhaps this may look like a lot, but just think of it like we are starting with the same fluid. They are of the same volume, right? We're just designating them V1, V2 based on the pistons. Then after this, you can now remember in this question we are focusing on areas, right? So you break these volumes into areas. You know that volume is going to be area times some distance times some length, isn't it? Exactly. So now you want to write the areas on one side, the distances on one side. There you do. Then we know that the other relationship that we have is that P1 is equals to P2, or the pressure on the small piston is equal to the pressure on the large piston. Therefore, we can say F1 over A1 is equal to F2 over A2. So we could do that, right? And then you then place the F's or rather the forces on one side, the areas on the other side. Then now you now come to the work now, the thing that we're trying to compare. So that's what we've done so far, right? Great. So uh so now we say the wake. Okay, let me just move the screen a little bit up. So now what we have there, so it's the wake one, wake two is equal to, so there we've got the F1. So we've got the F1, and then we've got the, yeah, so that's just wake. Remember wake is what? Wake is F1. Oh, sorry. Wake is force times distance, right? So here, just to differentiate them, we are saying F1 times distance 1, right? So F2 and the change in displacement or distance 2 there, right? So now, remember that so far we've actually made some derivations, right? Like remember from the working that we've done, we realize that okay, let's just separate them. You realize that we've got terms for what? For F1 and for F2, okay? We've got things that we've worked on earlier on, and we've also worked on something for the change in one and the change in two. We've also come up with something, right? And what did we come up with for F1 and for F1 over F2? We said, or you can check the working on top, but we said A1 A2 like that, right? And then for the distances, remember when we were relating with the areas, we said it was A2 over A1. So you can check the working and realize that's what we got, right? So now remember all this is coming from W1, W2. So what we are going to get, this cancels, this cancels, this cancels. So we are getting W1 over W2 is equal to 1. So cross multiplying therefore gives what? W1 equal to W2. So meaning the work being done by the small piston and the large piston, they are the same. So that's about it, right? So that's how you want to go about that one. So then, oh, so the one that's taking the screenshots, you're done. You've managed
Not
to take.
yet.
Okay, okay. Yeah, so now we are progressing to look at pressure measurements, and then we can look at or introduce Archimedes principle. So whenever we are measuring weights or rather pressure, there are two things we want to do. You can either want to measure the atmosphere or the pressure of the atmosphere, the atmospheric pressure, or you want to pressure or rather to measure pressure in an enclosed fluid. Okay, so you want to do those two things. So that's just what we are going to look at now. So, okay, so let's now draw our attention to what we have on the top right, or yeah, the top right corner. So we see that the PO there, we cannot see it. So that's atmospheric pressure, like we've already agreed. And now, so you see now there's some depth, right? Or there's some depth from the where the atmospheric pressure is up to the point B. So that means that the pressure at point B is higher than atmospheric pressure by what? By the PGH, right? Which is the density of the fluid, the gravity, and times that height. Okay, then now we know that when the fluids are the same points, like the way A and B are, that means that they have the same pressure, right? Great. Now, uh, if we calculate the pressure at B, which is atmospheric pressure plus PGH, or density G times height, what we are getting, we're going to get the absolute pressure, isn't it? So when we get uh, pressure is equals to PO, or atmospheric pressure, plus that pressure change, the density times gravity times height. When you get that value, it's going to be your what you call your what, your absolute pressure. Then if you then want to find the difference between the atmospheric pressure and the absolute pressure, what do? You are basically calculating PGH, isn't it? Or density gravity times what, times height. So what you do, you subtract the atmospheric pressure from the absolute pressure, then you're going to get what we call a gauge pressure. So that those are the terms explained right now. Let's now dwell on that a bit. So if the absolute pressure in the system is greater than atmospheric pressure, then H is positive. So what do they mean when they say H is positive? It simply means that where the point B is, or rather, if you want, you would say where that fluid is reaching, right? Like where that fluid is reaching, or the right hand column. So you can see where that fluid is, right? That fluid is higher than the what? Is higher than the lower fluid, isn't it? So you see that that fluid column is higher than the what? Is higher than the left hand column. So that tells you that the absolute pressure is greater, or more so when you see that the H is positive. So H being positive in this context means that you are able to have, after the atmospheric pressure, there is some depth, isn't it? So you've got some depth. So yeah, so going lower like that. So that's an important point that you'd want to remember. Then also, if so, sometimes they would ask to say, um, so they'll draw something for you like that, and then they will then ask you to say, so you see that pressure that we're having, that P there, the one which is pinkish, right? So now, sometimes they'll give you this and say, is the pressure in this greater or less than atmospheric pressure? So what would your answer be? Your answer would be what? Your answer is that it's greater. Why? Because the H is positive and the right hand column is greater than the what? Than the left hand column. So that's something that you want to do. Then if now you've got a situation where the right hand column is lower than the left hand column, then it means that the pressure, the absolute pressure in this system is less than atmospheric pressure. How do you know it's less than atmospheric pressure? The right column is going to be lower than the left. So what does that mean? It simply means that the atmospheric pressure is greater than the fluid, so much that it's able to move the fluid. It's able to move the fluid downwards and actually be able to what? To move it towards the left, right? And so increasing the right hand column. But because the pressure is higher in this system, this means that even though the atmospheric pressure is coming, it's failing to what? To press down this fluid. And we know that, yeah, that can only happen if the absolute pressure in this system is greater than what? Is greater than atmospheric pressure. So that's something that you want to take note of, right? So remember, this is a what? This is that's a manometer, right? And it's used to measure pressure in an enclosed fluid. Then another thing you'd want to look at is barometer. So when you talk about the barometer, what you're basically talking about is what we have on the top. Oh, sorry, not top. Okay, so that diagram that's remaining there, right? So that's the barometer. So for the barometer, what you are basically trying to assess is what? Is you are measuring the atmospheric pressure. So what you do is we're going to have a long tube which is closed at one end, and then you place it there. It's going to be almost a vacuum, right? And so its pressure can be taken to be zero. Now, because why is it a vacuum? So because it's almost a vacuum, and you know that if it's a vacuum, there is no air. If there's no air, then there's no pressure, right? So we know that our absolute pressure absolute pressure is equals to atmospheric pressure times pgh, right? Or density times gravity times height. Now we know that our absolute pressure is what? Our absolute pressure is what? Is zero. So if our absolute pressure is zero, it means that the pressure that this system is going to have, all of it is going to be what? All of it is going to be atmospheric pressure. So because what we are having is, remember, maybe let me just write this so that we can be able to appreciate it. So basically what we are having is this, huh? So basically what we are having is, remember we said absolute atmospheric pressure, then pgh, or density times gravity times height. Now remember, in the barometer we are having an almost like a vacuum, right, at the top. So the absolute pressure here is what? Is zero. So if the absolute pressure is zero here, what does this almost means we've got something like this, isn't it? But what's important for us really, it's not this negative, but it's just the very fact that the magnitude of the atmospheric pressure is equal to the what? Is equal to this. Okay, so this height is going to be this one here, right? So it's just the density of the fluid, which is usually mercury, and then the density, and then the what? And then the height, right? You can arrive at that. And so one atmosphere is defined to be the pressure equivalent to a column of mercury, which has got a height of what? 0.76 meters. So you know that if you set up a barometer and that height is 0.76 meters of mercury, and you know the density of mercury, and gravity remains the same, we can actually calculate a value for the atmospheric pressure. So let's just do that. So we are going to have atmospheric pressure. We know it's equal to the what? To density times gravity times height. So we know the density of mercury, some heavy metal. So we are going to have that, and then that's going to be that. So we are going to have that. Okay. And then you're also going to have 0.76, right? meters. So now what you're going to have 1.013 times 10 to power, so not power 3 to power 5, which is going to be our Pascal. And this is the same as 1 atmosphere, okay? So that's how you use a barometer. So the take home message is that a barometer measures the pressure of the atmosphere, whereas a manometer measures pressure in an enclosed fluid. And so these are the same things that, so that's why a manometer is used to measure blood pressure. Okay, so you see there, they're just an application, so they're measuring blood pressure, all because of this, the manometer, right? Because you're measuring the what? The blood pressure. That's a fluid. Your blood is almost like in an enclosed system, right? That's why whenever you cut a vessel, you bleed, you are losing fluid, right? But under normal circumstances, it's a closed fluid, isn't it? Yeah. So that's why you use a what? A manometer. But this is a more specialized one called a sphygmomanometer. So I think really for this one, that's where really the money is. Okay, so now when I can now, so just be like we introduced for chemistry, where we were introducing the Hess's law. So we'll just introduce the Archimedes principle. So yeah, so that's about it. I don't know if you've noticed that someone that's not able to walk, or someone that uses maybe a wheelchair, crutches, you see that when you place them in water, I think most can able to relatively stand, or at least they can be upright in water, right? So how does that happen? And maybe you may have noticed that it's easier to lift someone when you are in water than it is when you are just on surface, right? So how does all of this happen? It's because of Archimedes' principle, right? And the buoyant forces. So that's what we'll be looking at, right? But yeah, so that's basically what we'll be looking at tomorrow. But the take home point is that Archimedes' principle is very, very important because it helps us understand why someone, like I said, who uses crutches can be able to stand in water, or at least try to stand in water, and why it's easier to lift someone when you're in water than it is when you are on a dry surface, right? So those are some of the things that we'll be looking at tomorrow. So yeah, so that's basically what we'll be discussing.